Hi, how you doing? Welcome to today's lesson. What we're going to be looking at today is integration. Okay. People get freaked out about it, but it's not really that hard. If you know differentiation, integration is just a piece of cake. Okay. So when I start with integration, okay, the thing that I normally do with my classes, and I say, okay, great. If I know that dy by dx, okay, equals 2x, right? What would be the original function that would be able to give me 2x? And because by the time we get to integration, everyone has been doing differentiation over and over and over again, hopefully, okay? By the time we get to this, everyone should be able to just intuitively work out, well, what would differentiate to this? The thing that would differentiate to this would be x to the power of 2. Bring the 2 down, drop 1 from the power. Piece of cake. Okay, cool. Well, what about x to the power of 2 plus 3? Well, the derivative of that is 2x. What about x to the power of 2 minus 5? Well, the derivative of that is 2x. So can you see that plus any constant, plus any number at the end, if I differentiate anything with a number at the end, okay, that number is just going to disappear. So I don't really know what the number at the end is because I don't have any evidence at this stage what it could be. So what I do is I just go with this, plus c, plus some constant of integration, okay? Because if I had to differentiate that, that would disappear, right? Okay, differentiate it. You know how to do this, okay? All right. If however they said, what is this? The function that then passes through the point. What have I got there? 1, 2. It then passes through the point 1, 2. Well, that's a piece of cake. All I do is I plug 2 in for the y, I plug 1 in for the x, and I solve for c, and I get, in this case, c equals 1, I get 1 equals c. Therefore, my function that has this gradient that goes through this point is y equals x squared plus 1. That is my specific solution. That is my specific solution, my particular solution, when this gradient goes through that point. Okay. Otherwise, this is my general solution. Okay, please be careful of that. The most common mistake I see is people forget the c, and they just give, and they're asked to integrate this, they just give that. Right, super. So that's the rough explanation. Let's talk about integral notation, because it's pretty straightforward when you get used to it, but just to see it for the first time, sometimes it can be a little bit daunting. Okay, if this is your first time seeing integration, which I seriously doubt it is. So let's take a look at this. First thing, we start with a big S. Okay. Where this big S comes from, all right? I know it doesn't look like an S, it's an extended and squashed S, okay? But it comes from the Trapezium Rule. When you learn more about the Trapezium Rule, you can see that you can process the area underneath the curve as progressively smaller and smaller trapeziums. So you're taking the sum of the area of trapeziums and then you're taking that and tending it to infinity. You don't need to know that for now, we're just looking at simple integration, but it's useful to come back and look at that after you've done the Trapezium Rule. Okay, so there's that big S, the sum. Okay, and we're not putting in any 2 points here, we'll get that to when we get to definite integrals. Okay, but right now we've got the derivative, not the derivative, yes, the derivative, sorry, derivative, because you're going to the first function, derivative, whatever the differential equation is that you want, it can be more than one term, alright, and with respect to what dx, with respect to what variable you're using. Sometimes you'll have the integral of at with respect to t, for example, if you're integrating with respect to time, or whatever your independent variable is. Okay, awesome, so there that is. Now, this results in a formula that looks like this, alright? I've got x to the n plus 1, I add 1 onto the power, alright? Whatever the power is, I put 1 onto that, divided by that power, alright? Plus some arbitrary constant of integration. Okay, so x to the n plus 1 divided by n plus 1. Now the reason why I have to divide by n plus 1, because if I had to differentiate this, right, if I had to derive this guy to try and get back to there, look, I don't want any constant in front there. I want that to be 1. I want there to be no numerical coefficient in front there. If I had to differentiate this, this number would pop in front there. So how do I get rid of it? I divide that by the denominator, and that's what gets rid of it. Okay. So this is the general form for the integral equation. Right. So let's quickly do a couple. So if I want the integral of x squared dx, right? Well, this is very straightforward. X, I add 1 onto there, 3. I divide by that underneath 3, I plonk on my constant of integration. Done. Okay, if they said this went through the point 5,6, then I'd be able to solve for C, but right now, that's all I've got. Okay, so the integral of that is that. If you had to differentiate this, you would get that. Are you with me? Okay, undoing it. Awesome. So let's do one more, or a couple more. Let's do a slightly more tricky one. 3x plus 1 over x squared, 1 over x squared dx, all right, equals... Now, here's the thing I'm going to do. Oh, this reminded me of something. This works for everything except x to the negative 1, when x is the denominator, okay? The reason why is that because if I had to add 1 to the negative 1, this would become 0, and then divide by 0. You can't divide by 0, life ends, okay? So you cannot have a 0 up there. That's why it doesn't work with x to the negative 1. But there is a way around it, okay? We use logs with that. So don't stress about that. We'll get to that. It's slightly more advanced. Awesome. Let's just stick with everything except x to the negative 1. Alrighty, so here I've got x, this is not nice, let's make this x to the negative 2. So let's just rewrite this guy here. Let's rewrite them as the integral of, well, 3x, she's fine, and let's bring this to the top, plus x to the negative 2 by dx. Alright, and the nice thing about integration is the integral of, what did I say there? Integral of the sum is equal to the sum of the integrals, right? So compound integrals in that little note below, all I can do is integrate each one of these individually because they're just separate functions that are being added together. So I've got the integral of this is 3, right? There's my k, or my coefficient. I'm going to add 1 onto the power of 1 here, divide by that power, boom, right? Plus, right, now I'm going to do it messy and I'm going to tidy it up. I'm going to do 1 onto this, x to the negative 2 plus 1 is negative 1. Alright, divide by negative 1. Everyone with me? Okay, there it is. Now let's just tidy this guy up. Right, I've got 3x squared over 2. Well, that's fine to leave it as a top-heavy fraction. In algebra, we normally leave it as a top-heavy fraction. It's not an issue. Minus 1 over x. Okay, alright. So, there is our function where we integrate that to get to that. Okay, and this actually, what I've done here is I've used... Well, I've kept the k out, integrated this part, and then put the k back in. So I've used the second one in that note, in that purple note at the bottom there, right? Where the integral of a function with the coefficient is the same as the integral of the function, then put the coefficient back, okay? And then I've also used the first part of that purple note where I've actually split the integrals in my head. And I say, well, the integral of this plus the integral of that, boom. And they come together. Alright, I'm not going to go through that again, it's there in notes, it's pretty straightforward. Alright, then underneath that, in that green example, let's just do that green example because there's some cool points that I just want you to make sure that you're totally okay with. Okay, because, oopsie, come on. Love this thing. Because with that green example, there's a couple of tips that I would like to share with you. Right, so we've got the integral of t minus 3 over t. T minus 3 over t squared dt, right? Now, try not to, when you get more advanced, you can start doing it in here, alright? But for now, just multiply everything out, get them into separate terms, and work everything out from there. So if I multiply everything out here, I'm just going to first tidy up this bracket. So I've got the integral of t squared minus 6 plus 9t squared. T squared minus 6 plus 9 over t squared dt. I'm going to integrate it with respect to t. Alright? Super. So that's just multiplying out that bracket. And now I'm going to integrate each one of these. This one I'm going to put the negative t to the top. So I'm going to skip a line that I've actually got in there. Okay? Well, no. Let me put that in. The integral of t squared minus 6 plus 9t to the negative 2 dt. So firstly, multiply everything out, separate as much as possible, get all the x's into the numerator, okay, alright, by using the negative power laws, and then just integrate each one of this. So I've got t to the 3 over 3, right, minus 6 t to the 1, because this you can imagine as t to the 0. So this becomes 6t to the 1 over 1, if you want, alright, because there's t to the 0 there. Anything I can always rewrite times by t to the 0 is 1, right? And then I've got minus 9 t to the negative 1, alright? Or if you 1, you can put that over -1. So, but plus c, I almost did it, okay? So I've got t cubed over 3 minus 6t minus 9 over t. Awesome? Plus c. Plus c. Almost forget it. So there is my original equation. And the cool thing is that what you should try to do is take this one, differentiate this one, and make sure that you get back to that one. Okay, so if you have to differentiate this final example, you should get back to that one. Okay, so here's the tips. One more, very quickly. Firstly, multiply everything out to get them as separate as possible. Bring all the t's into the numerator, just like you would with differentiation if you're differentiating a polynomial. Bring all the t's into the numerator. Integrate each term separately. Remember your constant of integration. Tidy up. Done. Okay, go check out some more. This is the start of integration. It becomes a lot more fun after this. Okay, remember, I'm here for you.